Selecting objects is one of the most common operations in virtual reality, and research in this area identified techniques that work well for various situations. In a simple scenario where the objects are within the hand's reach, direct grabbing works well, and raycasting is great when objects are clearly visible but are difficult to reach. For more complex and dense environments, grid-based techniques such as expand and squat are good choices. However, object occlusion presents a problem, because selectables become only partially visible or not visible at all. In such environments, collision volume-based techniques, such as previously mentioned expand and squat, might still work, although with some limitations. These techniques reorganize the selectable objects into a grid, which means that positional information is lost. So, when multiple objects that look the same as the target are present in the environment, these techniques fail to provide the context to differentiate between the target and distractors. There have been attempts to address this problem, and a recent study evaluated a number of selection techniques that help with occlusion and found that lasso grid, alpha cursor, gravity zone, and magic ball were some of the best performers. Lasso grid allows the user to draw a trace, and all objects that fall within that trace are presented on a grid layout. User then selects with a ray. Alpha cursor turns the objects in a virtual environment transparent when they are at a threshold distance from the user. The user controls this threshold distance by tilting a joystick. This effectively moves a transparency wall towards and away from the user, revealing objects that are occluded in the environment. The actual selection is then done with raycasting. Gravity zone, instead of moving the wall, translates the objects themselves, and when those cross the invisibility wall, they become transparent. Selection is also done with raycasting. Lastly, Magic Ball creates a 3D minimap of all selectable objects inside a transparent sphere. The relative distances between the minimized objects is preserved. The user can select a group of objects using a resizable cursor, and objects from that area appear in a selection grid. As mentioned earlier, the issue with grid-based selection techniques is that they do not preserve the spatial information, which makes it difficult to distinguish same-looking objects from one another. Alpha Cursor and Gravity Zone attempt to deal with this, however they temporarily modify the original scene in the process. Further, the movement of objects or the wall is controlled with a joystick, so the precision and speed of these adjustments will depend on the controller gain. Overall, currently existing techniques can work for occluded environments, but they have some limitations. In our work, we attempted to improve the selection of occluded objects, and our solution to this problem combines cone casting, world in miniature, and grasping metaphors. It does not modify the original scene in the process and disoccludes the objects in a representation local to the user. We call our approach a projective interactive map. Our techniques consist of a highlighting cone that is used to point to a dense area of objects and a transparent shape that provides a live view on the currently highlighted area. For as long as the trigger button on the controller is held, live miniature representations of the highlighted objects are updated inside the transparent minimap. The objects' relative position to each other are preserved, as in the original scene. When the trigger button is released, objects inside the miniature representation freeze in place to allow for easier access to them. The user can now use his right hand to directly grab objects from the minimap. For additional visual cues, when the user's hand hovers over minimized objects, an outline appears around the original objects and its minimized copy. We created two versions of this technique that we call PIMs for short, for Projective Interactive Map, Disk PIM and Cylinder PIM. Cylinder PIM presents minimized objects in a cylinder that follows the user's left hand. This representation preserves all relative distances between the objects. The user can rotate the cylinder to bring the objects closer to make it easier to reach them. Disk PIM presents a flat round minimap, which means that the depth is lost, so when objects overlap in a user's view, they will also overlap in the minimap. To deal with this, when multiple objects in the minimap overlap with the grabbing hand, the participant can opt to freeze an additional copy of these objects on the circumference of the minimap. Because hovering over these copies outlines the original objects, this allows for very precise selections even without preserving the relative depth of the objects. To evaluate our new techniques, we conducted a user study where we recorded trial completion times for searching and repeat selection tasks. In the 4x3 within subject study, we compared 4 techniques across 3 object density levels. We compared disk PIM, cylinder PIM, gravity zone plus, and cone expand, which is a grid-based technique derived from the expand technique. We found that for searching, disk PIM was the fastest technique, and for repeat selection, cone expand was the fastest. However, no statistically significant difference between the two was found. For both searching and repeating, cylinder PIM also performed close to cone expand. Gravity zone was the slowest among the compared techniques for both searching and repeating. We believe that such results are observed because the minimap-based techniques preserve the spatial relationships between objects in the environment. But given that they require more steps to select the target objects, we need to check if this comes at a cost of more physical strain on the user. We collect a system usability scale and NASA TLX scores for all the techniques from participants during the study. All SAS scores were relatively high, and there were no significant differences between the techniques. NASA TLX scores were also relatively high, and a significant difference was found only in the effort measure, where Gravity Zone Plus was reported to require more effort by the participants than other techniques. These findings imply that both of our new techniques, cylinder PIM and disk PIM, can be effectively used for searching and selecting, and even though they require more steps to perform than other techniques, users did not report lower usability or higher load. Our techniques can be applied not only to selection with occlusion, but also to visualization. For example, in medical, chemical, or engineering visualizations, where it's important to preserve relative positions between atoms in a molecule or seed infrastructure parts. These techniques can also be extended to enable the insertion of objects into the environment, allowing for additional object manipulation. A limitation of our study is that we only evaluated the different techniques in a scenario where the target object was unique. In future work, we plan to run additional user studies to address this, and also to test new features, such as making the highlighting cone resizable and automatically spacing out overlapping objects inside the minimap. Overall, our results show that directly grabbing objects from an interactive map that displays live copies of highlighted portion of the scene is a viable alternative to other techniques that deal with occlusion in virtual reality.